The galaxy is 13 billion years old. Humans have been listening for 90. In that gap, entire civilizations could have risen, built empires across stars, and gone extinct before Earth even cooled. Tonight, you'll travel to a graveyard of dead signals, a sky full of ruins we cannot see, and a clock that may have already passed us by. If this pulls you in, hit like and subscribe so you don't miss what comes next. The Fermi paradox isn't asking where everyone is, it's asking when. Prepare yourselves. We begin. In the summer of 1950, a physicist named Enrico Fermi sat down to lunch with 3 colleagues at Los Alamos. They were talking about flying saucers. The conversation drifted to the size of the galaxy, the number of stars, the odds of life. Then Fermi went quiet, did some math in his head, and asked a question that has haunted science ever since. Where is everybody? The answer most people give involves space. The galaxy is huge. Distances are crushing. Maybe aliens exist, but we just can't reach each other across the gulf. That answer feels reasonable. It also misses the point entirely. Fermi's question had a hidden second half. He was not only asking where, he was asking when, and the when is far more terrifying than the where. Picture the galaxy as a giant theater. The stage has been open for 13 billion years. Civilizations are actors who walk on, perform their brief scene, and exit. The lights never dim. The show never stops. But here is the catch. Each actor only performs for a few minutes out of a 13 billion year run. If you walked into that theater at a random moment, what are the odds you would see anyone on stage? Almost zero. You would see an empty platform, dust drifting through the spotlight, and silence. Not because no one ever performed, because almost no one performs at the same time. This is the temporal version of the Fermi paradox, and it changes everything. When scientists talk about the search for extraterrestrial intelligence, they almost always assume the aliens are out there right now, broadcasting right now, waiting to be heard right now. Every radio telescope pointed at the sky operates on that assumption. The astronomers tuning into distant stars are listening for present tense voices. But the universe does not work in present tense. Light from the nearest star takes over 4 years to reach us. Light from the center of the galaxy takes 26,000 years. Light from the edge of the visible universe takes more than 13 billion. Every photon you have ever seen is a piece of the past, delivered late, sometimes ancient beyond comprehension. So when we listen to the sky, we are not hearing what is happening. We are hearing what already happened, sometimes recently, sometimes a million years ago, sometimes before life on Earth crawled out of the sea. This means the silence we hear could mean 2 completely different things. Either no civilization ever existed in the places we are listening, or many civilizations existed, sent their signals, and those signals washed past Earth long before humans built the first radio receiver. The second option is worse. It means the galaxy is not empty. It is full of echoes we missed, voices that called out into the dark and reached our solar system when there was nothing here but dinosaurs or trilobites or boiling lava. Fermi died in 1954. He never got to see his question grow teeth, but the teeth were always there, hidden in the math he ran in his head. The galaxy is old. Civilizations are brief. The chance that 2 of them overlap, even within a few thousand years, may be vanishingly small. The silence is not proof we are alone. It may be proof we are late. And once you understand that, the next question becomes unbearable. How late? Imagine showing up to a party that has been going on for 13 billion years. You walk in, the lights are still on, the music has stopped, the food is gone. There are no bodies, but there are scuff marks on the floor where chairs used to be. You ask if anyone is here. Nothing answers. That is roughly Earth's position in the galaxy. Our planet formed about 4.5 billion years ago. Life appeared maybe a billion years after that. Complex life, the kind that builds nervous systems and thinks, took another 2.5 billion years on top of that. Tool-using humans showed up roughly 300,000 years ago. Civilization, the kind with cities and writing, is around 6,000 years old. Radio technology, the only signal we have ever sent that could leave the planet, is about 130 years old. Now compare that to the galaxy itself. The Milky Way is roughly 13 billion years old. The first stars capable of forming rocky planets appeared maybe 11 billion years ago. That means Earth-like worlds could have existed for almost 3 times longer than our planet has been around. Some of them, by the laws of statistics, must have produced life. Some of that life, by the same laws, must have produced thinkers. Those thinkers had a head start on us, measured not in centuries but in eons. A civilization that began even 100 million years before ours would, today, be unrecognizable. Humans went from horse-drawn carriages to landing on the moon in 70 years. Imagine what a species could do with 70 million, or 700 million, or a billion, and yet we look up and see nothing. The standard reaction is to assume those civilizations never existed. That intelligent life is so rare it has only happened once, here, with us. But there is a darker reading. They did exist. They got their head start. They ran their experiment with technology, with energy, with expansion. And whatever happened to them happened a long time ago. The universe is not a level playing field where everyone starts at the same gun. The race began long before Earth had oceans. By the time our planet was warm enough for the first single cell, somewhere out there, a civilization may have already risen, peaked, and ended. Their entire arc, from cave fires to interstellar travel to extinction, could have unfolded while Earth was still a ball of magma. Their oldest archives, if they made any, would now be older than our continents. This is the part that bends the mind. Time in the galaxy is not measured in human lifetimes or even human histories. It is measured in stellar generations. Stars are born, burn for billions of years, and die. Civilizations are flickers between those long burns. They flash on, last a few cosmic seconds, and flash off. If a civilization rose 9 billion years ago, no trace of them would survive. Their planets would have been swallowed by their dying stars. Their machines would be dust. Their radio waves would have spread so far and so thin that the signal strength now would be indistinguishable from background noise. We are not just looking across space. We are looking across deep time, and the deeper you look, the more empty the sky becomes. Even more disturbing is what that emptiness implies about what comes next. Step into a backyard at dusk in the middle of summer. Fireflies blink across the lawn. Each one lights up for a fraction of a second, then goes dark. If you watched the field for an hour, you would see thousands of brief flashes scattered across space and time. No 2 flashes happen in exactly the same spot at exactly the same moment. Now, imagine those fireflies are spread across the galaxy, and instead of blinking once a second, they blink once every 100 million years. That is what the search for alien civilizations actually looks like. A civilization is a flash. It begins, it grows, it sends out whatever signature it can, and then it ends. Whether by collapse, by self-destruction, by transformation into something we would not recognize, or by simply outliving its own technology, the flash might last a few thousand years. It might last a few million. On a galactic timescale, either number is brief. Now, picture 2 such flashes. One happens in a star system 50,000 light-years away, 200 million years ago. The other happens in our own solar system, right now. Both are real. Both are technological. Both broadcast signals into the dark, but they will never see each other. The first signal washed past Earth long before our planet had birds. By the time we built radios, that civilization had been gone for almost as long as the dinosaurs. Their light is still traveling, of course. It has crossed into other parts of the galaxy by now. Maybe it reached some other listener. Maybe it reached no one. Either way, it is not coming back. This is the firefly problem in cosmic form. You can have a galaxy absolutely teeming with intelligent life and still have every single civilization feel utterly alone. The math allows for thousands of them to exist over the lifetime of the Milky Way without any two ever overlapping in time and space close enough to communicate. Astronomers sometimes call this the problem of synchronization. For a conversation to happen, two civilizations need to exist at the same moment, within a reachable distance, both with the technology to send and receive, and both willing to broadcast. Miss any of those conditions and the conversation never starts. The galaxy makes synchronization brutally hard. A civilization broadcasting from one side of the Milky Way needs roughly 100,000 years for its signal to reach the other side. If that civilization only lasts 10,000 years, the signal will outlive its makers by a factor of 10. By the time the message arrives, the senders are dust. This means the sky around us could be full of expired transmissions, letters from the dead, echoes from species that finished their entire history before we invented the wheel. You will not hear them by listening for live conversation. You can only hear them by listening for ghosts. And here is where the firefly metaphor turns dark. In a real backyard, even if no two fireflies blink in the exact same spot, you still see the field is alive. You see the pattern. You know they are there. In the galactic version, the flashes are so rare and so spread out that you might watch for 1,000 human lifetimes and never see a single one. The field would look dead, not because nothing is there, because you are watching at the wrong second. What if we have already missed every single flash that ever mattered? Here is a number that will quietly disturb you. The total length of time during which any civilization, including ours, can be detected from across the galaxy might be smaller than the lifespan of a single oak tree. That is the window of detectability. It is the slice of time during which a civilization is loud enough, advanced enough, and still active enough to leave a trace another civilization could spot. Before the window opens, the civilization is too primitive to make a mark. After it closes, the civilization is either gone or has moved beyond the kind of technology we know how to look for. For Earth, that window opened in the 1890s, when humans started using powerful radio transmitters. It has been open for about 130 years. How much longer it stays open is anyone's guess. Radio is already fading. In the early 20th century, broadcasts were enormous, blasted out at high power for miles in every direction. Anyone listening from another star with the right equipment could have caught the leakage. Today, signals are tighter, aimed, encrypted, and digital. They look more like static than messages. From a distance of a few light years, modern Earth is becoming quieter, not louder. If our radio era lasts only 200 years before being replaced by something else, that is the window. 200 years out of 4.5 billion years of Earth history. A flash so brief it barely registers. Now scale that up. Imagine every civilization in the galaxy has roughly the same window length. 200 years of being detectably loud. Then maybe they go silent, either because they collapse or because their technology evolves past radio and into something we cannot pick up. Pinch a civilization's audible life down to 200 years. Spread civilizations across 13 billion years of galactic history. The odds that any two of them are loud at the same time, in places close enough to hear each other, become brutal. It is like trying to have a phone conversation where each person is allowed to speak for 2 seconds, randomly, sometime in the next century. You would never connect. This is why the silence we hear from space is not strong evidence that no one is out there. It is evidence that almost no one is currently within their detectable window, pointed our way, with us listening at the right moment. The window matters for another reason. It works in both directions. If our civilization closes its own window, either by going extinct or by quietly outgrowing radio, then any aliens looking for us in the future will see Earth go dark. To them, we will become another cold rock orbiting an ordinary star. No signal, no proof we ever existed. Some scientists worry this is happening already. Earth's radio leakage peaked in the 1960s and 70s. It has been getting weaker every decade since. If you graphed Earth's broadcast volume over time, the line would rise sharply, hit a peak, and start sloping down. Our window is contracting in real time. So, when astronomers say the galaxy seems quiet, they may be hearing something true. Civilizations are quiet. They are quiet most of the time. They are quiet most of their existence. They only get loud, briefly, in the middle. And the middle, for any given species, is shockingly short. Lift your wrist and look at your watch, or your phone, or any clock nearby. The second hand sweeps once. That single sweep, in galactic terms, is roughly how long humans have been technologically loud. 130 years. That is the entire span of our radio age. From the first crude wireless experiments at the end of the 1800s to right now. In that time, humans went from horse-drawn streetcars to satellites mapping the surface of Mars. We split the atom, sequenced our own genome, and built machines that talk to each other across oceans. Every part of modern life, the part that would look like alien magic to someone from the year 1800, fits inside that 1 century and a third. Now ask yourself how that compares to anything else. Earth has hosted life for around 3.5 billion years. Mammals have existed for 200 million. Our own species, Homo sapiens, is roughly 300,000 years old. Civilization, with cities and writing, is 6,000. Industrial civilization, the kind that burns fuel and broadcasts signals, is about 250. The detectable, loud, broadcasting human civilization is 130. Stack those numbers next to 13 billion years of galactic history and the picture becomes painful. The fraction of Earth's existence during which Earth has been a radio source is so small it is almost a rounding error. Anyone scanning our solar system from far away has had a near zero chance of catching us during our broadcast window. To make this concrete, imagine compressing the history of Earth into 1 calendar year. The planet forms on January 1st. Single-celled life appears in late February. Multicellular life shows up in mid-November. Dinosaurs walk in late December. Humans evolve about 30 minutes before midnight, on December 31st. The first radio broadcast happens in the last quarter of a second before the year ends. That is our flash. A quarter of a second on a calendar of a single Earth year. And the galaxy is older than Earth by a factor of 3. This is why the window matters so much. We are not just briefly visible, we are barely visible at all, and we are getting harder to spot. In the 1950s, American television and radio leaked enormous amounts of energy into space. Old shows, old commercials, old news broadcasts blasted outward in every direction. That bubble is still expanding. It is currently about 70 light-years across, which sounds impressive until you remember the galaxy is 100,000 light-years wide. Our loudest signals have reached about 0.1% of the Milky Way. Inside that bubble, our broadcasts are also getting weaker the farther they travel. Radio signals fade with distance. By the time a 1950s sitcom reaches a star 50 light-years away, the signal is so faint you would need a receiver the size of a small city to detect it clearly. Now look forward instead of backward. If humans last another 500 years, our window might close. We might switch entirely to fiber optics, tight beam lasers, and quantum communication that leaks almost nothing into space. Earth would go silent again, not because we died, but because we grew up. Future aliens scanning our system would see a quiet rock with nothing notable about it. They would have missed us by a few centuries. The terrifying part is realizing every other civilization may have done the same. There is a difference between an empty room and a room full of corpses. Both are silent. Both have no living voices. But one of them has stories pressed into the walls, faint impressions left behind by people who used to be there. The galaxy may be the second kind of room. For most of the 20th century, when scientists talked about extraterrestrial silence, they pictured a universe that simply never produced thinking creatures. Maybe Earth was a freak accident. Maybe the conditions for life are so impossibly precise that we are the only experiment that ever succeeded. That picture is comforting in a strange way. It makes humanity special. It frames our loneliness as proof of our uniqueness. The temporal version of the Fermi paradox suggests something much harder to swallow. What if the silence is not because no one was here, but because everyone has already left? Consider the timeline. The Milky Way has been around for about 13 billion years. The first generation of stars, made almost entirely of hydrogen and helium, did not have the heavy elements needed for rocky planets and life as we know it. But by the second generation, those elements existed. Stars began forging the building blocks for biology. Planets began to form with iron cores, water oceans, and carbon-rich atmospheres. Astronomers estimate that planets capable of supporting life could have existed as far back as 8 to 10 billion years ago. Earth, by comparison, is only 4.5 billion. We are not the first opportunity. We are one of the most recent. Now, imagine even one civilization rose during that earlier window. Imagine they reached the level of technology humans have now and kept going for another 1,000 years, or 10,000, or 100,000. Whatever they built would have completed its lifespan and decayed long before our solar system condensed out of its dust cloud. Their cities, if they had cities, would be older than our oldest mountains. Their radio signals would be so spread out across the galaxy that they would now be indistinguishable from background noise. Their satellites, if any survived, would have decayed into dust the size of sand grains. Their planet itself might have been swallowed by its expanding sun. There would be nothing left to find, not because the civilization was small or short-lived, but because too much time has passed. This is the graveyard model of the galaxy. It does not say life is rare. It says life is common, but recoverable evidence of life is fragile. Civilizations leave traces, but those traces erode. Stone fades. Metal corrodes. Atmospheres get scrubbed by stellar wind. Radio waves dilute into nothing. Even on our own planet, civilizations only a few thousand years old have crumbled into pieces. Archaeologists struggle to read. Stretch that decay across millions or billions of years, and you get a sky full of vanished neighbors. The galaxy may not be a place where intelligence is rare. It may be a place where intelligence is constantly being born and constantly disappearing, and the gap between any two flashes is wider than the lifetime of all the stars currently visible. When you look up at the night sky, you may not be looking at empty real estate. You may be walking through a cemetery that stretches for 100,000 light years, with headstones too far apart to read. And our headstone is being carved right now. Look up tonight at the brightest star in the sky. Whatever it is, you are not seeing it. You are seeing its past. Light travels fast, but the distances in space are so absurd that fastness barely helps. Light from the sun takes 8 minutes to reach Earth. So when you look at a sunrise, you are looking at sunlight that left the sun while you were still in bed, brushing your teeth or pouring coffee. Step beyond the sun and the delays become brutal. The nearest star, Proxima Centauri, is just over 4 light years away. The light hitting your eyes from that star tonight left it in the year 2022. Sirius, the brightest star in the night sky, is about 8.5 light years away. The image of Sirius you see right now is from the late 2010s. Push further. Polaris, the North Star, is around 430 light years away. The light arriving from it left during the time of Galileo. Anything happening at Polaris in the present day, any explosion, any flare, any signal, will not reach Earth until the year 2450. Now extend that to the rest of the galaxy. Stars in the disk are tens of thousands of light years away. Some are over 100,000. The galaxy you see in a long exposure photograph is a layered image, not a snapshot. The closer stars show recent events. The farther ones show ancient ones. The center of the galaxy, glowing in those photos, looks the way it looked 26,000 years ago. Whatever is happening in the galactic core right now, you will not know about it until the year 28,000 or later. This is what astronomers mean when they say the universe is a time machine. Every photon that hits your eye is a courier carrying old news. The faster something moves, the older the news gets, the farther you look. For the search for alien civilizations, this changes the entire game. If a civilization exists in a star system 1,000 light-years away, anything you detect from them today is from 1,000 years ago. They might still be there, broadcasting, building, thriving, or they might have collapsed 999 years ago, and you are picking up the last signal of a dead world. You have no way to tell the difference until you wait 1,000 years for new information to arrive. If the civilization is 10,000 light-years away, the gap becomes terrifying. Whatever you see is 10,000 years stale. That is longer than human civilization has existed. An alien species could rise, build empires, fight wars, master fusion, and go extinct, all within the time it takes their light to reach us. This is why some scientists say the sky is full of ghosts. Every detectable signal is a recording. Every flash of intelligence is an echo. And echoes, by definition, mean the source has already moved on. It also means our own signals, the ones we have leaked since the 1890s, are still expanding outward. Right now, somewhere 50 light-years away, an alien with the right equipment could be hearing the very first radio broadcasts ever made on Earth. To them, the height of human civilization is wax cylinders and Morse code. We are someone else's past. They are somebody else's. The whole galaxy is layered in time, and no two observers ever share the same moment. The silence we hear may be the loudest part of the past. Take all of cosmic history, from the moment of the Big Bang to right now, and squeeze it into a single calendar year. This is a thought experiment astronomers love because it forces the human brain to feel something the numbers cannot deliver. The Big Bang happens at the first second of January 1st. The universe begins to expand. Hot plasma cools into hydrogen and helium. By late January, the first stars ignite. By March, the earliest galaxies are forming. The Milky Way, our home, takes shape sometime around May. The sun does not exist yet. Most of the year passes with stars being born, dying, and seeding the universe with heavier elements. Generations of suns rise and explode. Their dust gets recycled into new stars and new planets. By the time September arrives on this cosmic calendar, the universe is already older than the entire future of Earth will be. The sun finally lights up around early September. Earth forms a few days later. Life appears on Earth in late September. For most of October, November, and into December, that life is microscopic, single cells multiplying in oceans. Nothing complex, nothing thinking. Multicellular life arrives in mid-November. Plants colonize land in late November. Dinosaurs show up around Christmas Day. They die out on December 30th. Mammals expand. Primates appear. By late afternoon on December 31st, the first humans evolve. All of recorded human history fits in the last 14 seconds of the year. The Roman Empire rises and falls in the final 5 seconds. Industrial revolution happens in the last second. Radio is invented in the last quarter of a second. The internet, smartphones, space probes, and modern civilization all happen in the last few hundredths of a second before the year ends. Now, overlay this calendar with the search for alien intelligence. If an alien civilization had risen and fallen during October, their entire history would be over before mammals even existed on Earth. They could have built starships, mastered energy, lived for millions of years, and gone extinct, all while our planet was a dim ball of bacteria. By the time humans showed up to look around, that civilization would have been gone for the equivalent of 2 cosmic months. Nothing left, no ruins, no signals, just the chemical scars of long-dead worlds. If a civilization is rising right now, on December 31st at 11:59 and 59.9 seconds, simultaneous with us, they would still be 100 or 1,000 light-years away in real space. Their light would not reach us for centuries. This is what the cosmic calendar reveals that the standard Fermi paradox misses. We are not asking why no one is around. We are asking why no one is around in the same fraction of a second. The galaxy is full of months. We are listening for a single instant. Even if 1,000 civilizations had risen across cosmic history, the chance that any of them happens to be loud and reachable during our specific quarter second is so small it stops feeling like a probability and starts feeling like a wall. We have arrived to a party that has been running for billions of years, walked into the room exactly as the last guest leaves, and stood there wondering why the lights are on but no one is talking. What if the next guest does not arrive for another 100 million years? The first dinosaur walked the Earth about 240 million years ago. They ruled for 175 million years before an asteroid ended their reign. That is a long stretch by any human measure. But on the galactic timeline, an entire intelligent civilization could have risen and fallen before the first dinosaur ever took a breath. This is the part of the time-shifted Fermi paradox that breaks something inside the mind. It is one thing to picture an alien species that lives somewhere far away right now. It is something else to picture them existing not in another part of space, but in another part of time, and being just as gone as the dinosaurs are gone, with even less left behind. Consider what the galaxy looked like 300 million years ago. The Milky Way had been around for over 12 billion years. Stars older than the Sun had already been burning for billions of years, with their planets stable, weathered, and old. Some of those planets, statistically, would have hosted the same chemistry that produced life on Earth. Some of that life, statistically, would have evolved complex nervous systems. Some of it would have built tools. 300 million years is enough time for everything. From single-celled algae to spacefaring intelligence is, on Earth, less than 1 billion years. Cut that in half and you still have civilizations rising before our planet had reptiles. Now imagine one of those civilizations completed its arc, built radios, sent probes, maybe colonized a few nearby stars, and then, like every empire ever known, ended. 300 million years later, what would be left? Almost nothing. A radio signal sent 300 million years ago has now traveled 300 million light-years. The signal is so spread out that the energy hitting any given receiver is below the threshold of detection. It is still technically there, but indistinguishable from noise. You could have a sky full of these dead transmissions and never know. A probe launched 300 million years ago, even one that traveled at 1% the speed of light, has covered 3 million light-years. That is 30 times the diameter of the Milky Way. It is in another galaxy by now, or drifting in the empty space between galaxies, or smashed into something in the dark. A planet they once lived on has had its tectonic plates churn through hundreds of cycles. Mountains have eroded, continents have shifted, cities, even concrete and steel ones, would have been pulverized and recycled into the planet's crust. There would be no archaeology, no fossils, no surface clues at all. The atmosphere, if it ever held strange industrial gases, would have been chemically scrubbed by ultraviolet light and stellar wind. Any isotopic fingerprint of advanced technology would be diluted past the point of measurement. Their entire existence would be a story with no surviving witnesses, not even a ghost, just absence. This is the horror of deep time. The galaxy may have hosted thousands of civilizations like this, each rising in its own brief flash, each leaving evidence too fragile to outlast the next 100 million years of cosmic erosion. By the time another civilization rises to look for them, the trail is already cold. We are looking for neighbors who lived in the same neighborhood. The temporal Fermi paradox suggests we are looking for neighbors who lived in the same neighborhood several Earth ages ago, and whatever made them disappear may be coming for us next. There is a name for what happens when two civilizations exist, but never overlap enough to communicate. Some scientists call it temporal isolation. The phrase sounds clinical. The reality behind it is one of the loneliest ideas ever proposed. Temporal isolation says that even in a galaxy crowded with intelligent life, the cosmic clock makes contact almost impossible. It is not that the aliens are hiding. It is not that they are too far. It is that the moment when their existence and ours could have meaningfully crossed has either already passed or has not yet arrived. To picture it, imagine a long hallway with thousands of doors on either side. Each door represents a civilization. The doors open and close at random times across 13 billion years. When a door is open, the civilization exists. When it closes, that civilization is gone. Now imagine you walk down the hallway, but you are only allowed to be there for 1 second. During that single second, how many doors are open at the same time as yours, close enough for you to see inside? The answer, given the math of brief civilizations spread across deep time, may be 0. This is what makes the temporal version of the Fermi paradox so much heavier than the spatial one. The spatial version says aliens are far, distance is fixable, send a probe, wait, build a bigger telescope. Eventually you cross the gap. The temporal version says aliens are not in your time. There is no telescope big enough to cross that. Time only moves one direction. You cannot travel into the past to meet a civilization that died before yours began. You cannot wait for a future civilization that has not yet evolved. Even if they leave messages, those messages must survive the geological erosion, the cosmic ray bombardment, and the simple thinning of any signal across light years. The walls between civilizations may be made of years, not miles. This is why some researchers argue the Drake equation, the famous formula for estimating how many alien civilizations exist, is incomplete. It includes the number of stars, the fraction with planets, the chance of life, the chance of intelligence, the chance of communication. What it underweights is how long any civilization stays in the loud, detectable phase. If that phase is short, the equation can produce a galaxy bursting with life that is still functionally empty from any single observer's point of view. Picture a ballroom. 10,000 dancers cycle through the floor over the course of a night, but each one only stays for a few seconds before leaving. At any given moment, the floor looks empty. You could walk in, look around, and conclude there were no dancers. You would be wrong. They were there. They are just never there at the same time. Earth may be in the empty middle of one of those moments. The dancers came before us. The next dancers will come after. We see an empty floor and call it proof of solitude. There is a darker version of this idea. Some scientists worry that the brief lifespan of civilizations is not random. It might be a feature of intelligence itself. Once a species reaches the technological level we have now, it may have a high probability of destroying itself within a few hundred or few thousand years. If that is true, then the civilizations that flicker on the galactic stage are not just brief because of cosmic accident. They are brief because intelligence does not survive itself, in which case, the loneliness is not just a feature of time, it is a warning. Imagine 2 ships sailing across an ocean so vast that crossing it takes 1,000 years. Each ship is crewed for only a few decades. Then the crew dies out and the ship drifts on, empty, until it runs aground or rots away. Now imagine 1,000 of these ships have sailed across that ocean over the past 100,000 years. What are the odds that 2 of them passed close enough, while both still crewed, to wave at each other? Almost 0. This is roughly what missing each other by 1,000,000 years looks like in the galaxy. 1,000,000 years sounds like a lot. To a human, it is unimaginable. Our entire species has only existed for about 300,000. 1,000,000 years is more than 3 times the age of Homo sapiens. But on cosmic scales, 1,000,000 years is a single tick of the second hand. The Milky Way has been spinning for 13,000 of those ticks. A civilization that existed 1,000,000 years ago is, by any galactic measure, our contemporary, and we still cannot reach them. Here is the problem. If a civilization rose 1,000,000 years before ours and lasted for, say, 100,000 years, their entire run ended 900,000 years before humans figured out fire. Their radio signals, if they used radio, washed past our solar system long before our species existed. Their probes, if they sent any, traveled in directions we have no way of tracking. Their planet may have moved due to stellar drift, the parent star slowly orbiting the galactic center, while the rest of the galaxy turned around it. Even if their physical infrastructure still exists somewhere, the geological and astronomical changes over 1 million years would have erased most surface evidence. New craters formed, old continents shifted, asteroid impacts wiped specific regions clean. 1 million years is enough time for any planet to dramatically reshape itself. So when we point our telescopes at the star where they used to live, we see a star, maybe a planet, maybe even an atmosphere. We do not see them. We see what is there now. This is why temporal misses are so devastating. Even small ones, by cosmic standards, are total. Miss by 1,000 years and you might still detect old signals. Miss by 10,000 and the signal is too faint to pick out. Miss by 100,000 and the entire infrastructure has decayed. Miss by 1 million and there is essentially nothing left to find. Now multiply this by the number of civilizations that may have existed across the galaxy in the past few billion years. If even 10 arose at different times, separated by 1 million or 2 each, none of them ever met. Each one rose, looked around, found silence, and assumed it was alone. Each one died believing it was the first or the only. We are doing the exact same thing right now. We point our telescopes outward, hear silence, and slowly build a worldview around the idea that intelligence is rare. We may be the 10th species in this galaxy to do that, or the 100th. Each previous one drew the same conclusion. Each previous one was wrong. The galaxy has been running this experiment for billions of years. It keeps producing thinkers. It keeps separating them by walls of time so thick that none of them ever realized the others existed. If this is true, the silence is not a clue about the universe. It is a clue about us, about how isolated thinking creatures naturally are, and about how easy it is to mistake your loneliness for proof. A radio signal does not vanish. It dilutes. Picture dropping a single drop of red dye into a swimming pool. At first, the dye is concentrated. You can see it clearly, a small bright cloud near where it landed. Then it spreads. It thins. After a few minutes, the entire pool has a faint pink tint, and that tint is so subtle you almost cannot see it. The dye is still there. Every molecule is still in the pool. You just cannot pick it out anymore. Now imagine that swimming pool is the galaxy, and the dye is a radio broadcast. The same thing happens, only the pool is 100,000 light years across. When a radio signal leaves a planet, it spreads outward in all directions. The energy that started at the transmitter gets smeared across an expanding sphere. Every time the radius doubles, the energy hitting any given square inch drops to 1/4 of what it was. By the time a signal has traveled 100 light years, the per square inch power has dropped by a factor of millions. By 1,000 light years, billions. By 10,000, the signal is so faint that distinguishing it from natural background noise becomes a brutal task. This is called the inverse square law, and it is the great enemy of every interstellar conversation. It means the most powerful broadcasts ever made on Earth, the loud television and radar transmissions of the mid-20th century, are already barely detectable, just a few dozen light years away. By the time those signals cross the galaxy, they will be indistinguishable from cosmic static. There is another problem: time. A radio wave does not just spread outward, it also keeps moving. It does not pause when it reaches a star. It keeps going. So, a signal sent from Earth in 1960 is currently 65 light-years away, expanding into a thinner and thinner shell. It has already passed every star within 65 light-years that was watching at the right moment. If those watchers blinked, the signal moved on. They will not get another chance. Layer this on top of the time problem. A civilization that broadcasts for, say, 200 years creates a shell 200 light-years thick, expanding outward at the speed of light. Anyone outside that shell hears nothing because the signals have not arrived yet. Anyone inside the shell hears the broadcast only during the brief moment the shell passes through their location. After that, silence again, So even a loud civilization is only loud to a specific listener for a specific window of years. Before the shell arrives, they hear nothing. After it passes, they hear nothing. And the shell gets fainter the farther it travels, until eventually it is too faint to detect at all. This means a galaxy could be full of civilizations that all broadcast at different times. And from any one observer's point of view, the sky still looks empty. The shells from older civilizations have already passed. The shells from current civilizations have not yet arrived. The shells from nearby civilizations are too brief to catch unless you happen to be listening at the exact right second. Add in the fact that signals also lose strength because of interstellar gas, dust, and magnetic fields, and the picture gets worse. A signal traveling thousands of light years gets distorted, scattered, and absorbed along the way. By the time it reaches a distant listener, even a powerful original transmission may be unrecoverable. Every civilization that ever broadcast is, in a sense, slowly suffocating. Their voices are being eaten by space and time. Eventually, they fall below the noise floor and disappear forever. That is the quiet horror of looking up at the sky. The voices may be there. They are just dying. In the 1960s, a physicist named Freeman Dyson proposed an idea that has haunted science fiction ever since. A civilization advanced enough, he argued, would eventually need so much energy that the only practical source would be its own star. And the most efficient way to capture that energy would be to surround the star with a vast structure designed to absorb every photon it produces. This came to be known as a Dyson sphere. Not a single solid shell, but a swarm of orbiting collectors, panels, or habitats, dense enough to harvest most of the star's output. To anyone watching from far away, the star itself would look strange, dimmed in visible light, glowing instead in infrared, where the captured energy radiates back out as waste heat. Astronomers have looked for these objects, not because they expect to find them, but because they should be detectable. A star that is missing in visible wavelengths and bright in infrared would stand out. It would be a fingerprint of an industrial civilization at the highest scale. So far, no clear examples have been found. The standard reaction is to say Dyson spheres do not exist because civilizations capable of building them do not exist. But the temporal Fermi paradox suggests another possibility, much darker. What if Dyson spheres do exist, and they are cold? Stars do not last forever. A star like our Sun has a lifespan of about 10 billion years. It burns hydrogen, then helium, eventually expanding into a red giant before collapsing into a white dwarf and slowly fading. Smaller stars last longer. Larger ones die faster. Either way, every star has an expiration date. A civilization that builds a Dyson sphere is, by definition, tying its survival to its star. Even if the civilization itself lasts millions of years, eventually the star will exhaust its fuel, change phases, and begin to die. The Dyson sphere will start to fail. Energy collection will drop. The civilization will be forced to migrate, downsize, or end. If that happened 1 billion years ago, somewhere in the galaxy, what would be left? The civilization is gone. The star is gone, or transformed into something dim. The Dyson swarm, if it ever existed, has had 1 billion years to deteriorate. Its components, originally built to last, have been hit by micrometeorites, cooked by solar wind, and twisted by gravity. Pieces have spiraled inward and been swallowed. Other pieces have drifted outward into the dark. What remains is a cloud of debris orbiting a dead star. To a modern astronomer, it looks like nothing special. Maybe an unusual asteroid belt, maybe a strange dust ring. Definitely not a sign of intelligence. The galaxy may be littered with cold Dyson swarms, each one a monument to a civilization that solved its energy problem, lived for a long time, and then disappeared. Each one now too eroded, too cold, too far past its prime to look like anything but natural debris. This is the kind of evidence the temporal Fermi paradox predicts. Not bright lights in the sky, not active machines, just leftovers. Quiet, decayed, unremarkable from a distance. If you were a paleontologist looking for dinosaur bones, you would not expect to find a living Tyrannosaurus. You would expect to find scattered fragments, half buried, half eroded, easy to miss if you did not know what you were looking for. The galactic equivalent may be dim infrared excesses around old stars, strange dust patterns in places where dust should have settled, anomalies most astronomers explain away as natural variation. Somewhere out there, the bones may already be in our data. Two questions sit at the heart of the temporal Fermi paradox, and they pull in opposite directions. Is humanity late to the galactic party, or are we early? Both possibilities are unsettling. Each one tells a different story about what happens to thinking species in this universe. The late hypothesis says we are showing up after the show is mostly over. The galaxy had a window roughly 5 billion years ago when the conditions for life were ideal. Stars had stabilized, heavy elements had spread, planets with the right chemistry had formed. Civilizations could have arisen and reached technological maturity long before Earth even existed. If this is true, the silence we hear now is the silence of a galaxy past its prime. Most civilizations have already had their run. The big builders, the pioneers, the species who would have left the deepest marks, all came and went while our planet was still cooling. We are walking through the ruins of an ancient garden, too late to see it bloom. The early hypothesis flips that on its head. It says we may actually be among the first. This idea comes from looking at the universe's overall timeline. The universe is about 13.5 billion years old. The longest-lived stars, small red dwarfs, will keep burning for trillions of years. Most of the time available for life to exist in the universe has not yet happened. The vast majority of stars that will ever support life are either still forming or have not yet had time to evolve thinkers. If you were a betting cosmologist, you might argue that intelligent life is most likely to appear later in the universe, when conditions stabilize and red dwarfs settle into long, quiet burns. By that logic, humanity is showing up early. We are among the first wave, with most future civilizations still hundreds of billions of years away from existing. Both hypotheses solve the silence in different ways. Both are also terrifying. If we are late, then the universe has already produced most of its intelligence and lost it. Whatever happened to those civilizations is what eventually happens to all of them. We are not part of a beginning. We are part of an ending. And the silence around us is the natural state of a universe that produces thinkers and then watches them go quiet. If we are early, we face a different kind of fear. The universe is built for life on a much longer timescale than ours. We are the first generation of guests in a house that will eventually fill up. Most of what we do, every signal, every probe, every attempted message, will be sent into a sky that has no listeners yet. Our broadcasts will arrive at empty stars and empty planets, not because life is rare, but because life has not yet evolved there. In either case, we are alone. There is a third possibility, and it may be the most uncomfortable. Maybe humanity sits in a brief, narrow gap between two waves. The first wave came and went billions of years ago, leaving traces too eroded to find. The next wave is still hundreds of millions of years away, sleeping in single-celled forms on planets that have not yet stabilized. We are in the trough between waves. The sea is calm. The horizon is empty. There is no one to call to and no one to answer. Whichever scenario is true, the silence is no longer a mystery about distance. It is a question about timing. And timing, unlike distance, does not yield to any technology we know. In 2021, a small group of scientists, led by economist Robin Hanson, published a paper that quietly reframed the entire Fermi paradox debate. They called their idea the Grabby aliens model, and despite the strange name, the math behind it is brutal. The model starts with a simple assumption. If intelligent civilizations exist, some of them will try to expand. They will build colonies. They will spread to nearby stars. They will use up resources and keep pushing outward. Once a civilization becomes grabby, meaning it actively expands and rearranges its environment on a large scale, it leaves a fingerprint that should be detectable across vast distances. The Grabby aliens model then asks a simple question. Given the age of the universe and the speed at which expansion could happen, where are the borders of grabby civilizations right now? The answer is uncomfortable. If grabby civilizations exist and expand at a fraction of the speed of light, their borders should already be visible in our skies. We should see entire regions of space transformed, stars dimmed by Dyson swarms, galaxies rearranged for energy harvesting, whole sections of the cosmic background lit up with the heat signatures of industrial-scale activity. We do not see this. The sky looks natural. Galaxies look untouched. Stars burn the way physics says they should burn, with no obvious tampering. The Grabby aliens model interprets this lack of evidence in a specific way. It says, we are in a window where grabby civilizations have not yet reached us, but they may already exist and be expanding. We just happen to be sitting in a region of the universe their expansion has not yet swept through. Run the math, and the model produces a prediction. Grabby civilizations should appear roughly once every billion years per galaxy, and they should expand fast enough to fill significant portions of the universe within a few 100 million years of starting. From our position, we should expect to find ourselves in one of the last untouched regions, with grabby borders sweeping toward us at relativistic speeds. In other words, the silence is not permanent, it is temporary. Somewhere out there, the borders are already moving. The model also makes a darker prediction about timing. It says civilizations that become grabby tend to do so early in their development because the longer they wait, the more competition they face. This suggests humanity is, statistically, behind schedule. If most civilizations expand within a few thousand years of becoming technological, and we have been technological for 130 years without expanding, the clock is ticking. There is another implication built into the math. If grabby civilizations are real, the gap between us and the nearest one may be shrinking right now. Their expansion, even if it started millions of years ago, is on a relativistic timeline. Their borders might be a few 100 million light years away, or they might be much closer, with the news of their arrival still on its way to us, traveling at the speed of light from the moment they crossed into our cosmic neighborhood. The Grabby aliens model does not predict friendly visitors. It does not predict hostile invaders. It simply predicts neighbors who reshape everything around them. A civilization that becomes grabby is, by definition, one that uses cosmic resources at a scale that changes the surrounding universe. Whether they care about Earth or not, their arrival would change everything we see. The most chilling part of the theory is its conclusion. We are probably late. Other civilizations are probably already expanding, and the silence we hear may be the calm before an arrival we cannot stop or even prepare for. The galaxy may not be empty. It may be quiet because we are the territory next on the map. In 1949, mathematician John von Neumann proposed a strange idea. What if you built a machine that could replicate itself? Not a living thing, but a device. Send one out into space. It finds raw materials. It builds copies of itself. Those copies travel further and do the same. Within a few generations, the original machine has become a swarm spreading outward at exponential speed. These are now called von Neumann probes. The math behind them is what makes them terrifying. If a single civilization launched self-replicating probes traveling at even 1% the speed of light, those probes would saturate the entire Milky Way in about 10 million years. 10 million years sounds long. On galactic scales, it is nothing. The galaxy is more than 1,000 times older than that. This means any civilization that ever decided to send out self-replicating probes anywhere, anytime, in the past few billion years should have already filled the galaxy with them. The probes should be in our solar system. They should be on the moons of Jupiter. They should be in the asteroid belt. They should be everywhere. We see none. This is sometimes called the silence of the probes, and it tightens the temporal Fermi paradox into a single sharp question. If the technology is possible, and the timescales are short enough that even one probe-launching civilization in the past billion years should have saturated the galaxy, then where are they? There are several answers, each darker than the last. The first is that no civilization has ever launched probes. This is hard to believe. Humans have already discussed the idea seriously. We are within a few centuries of being able to attempt it. If even one civilization in galactic history made it past our current technological level, the temptation to send out exploratory probes would have been enormous. The fact that none did is either a coincidence so unlikely it strains belief, or evidence that something stops civilizations before they reach that point. The second answer is that probes were launched, but they failed. Self-replicating machines may be harder to build than the math suggests. They might break down, get damaged, or simply stop replicating after a few generations. If every probe-launching civilization in history hit the same engineering wall, the galaxy could appear empty, even with thousands of attempts. The third answer is that the probes are here, but we cannot recognize them. They might be extremely small. They might be hidden inside asteroids. They might be lying dormant, waiting for something specific to wake them up. They might have already passed through our solar system millions of years ago and continued onward without leaving a trace we know how to read. The fourth answer is the one that quietly disturbs scientists the most. Probes are not here because they were stopped, maybe by another, older civilization that watches for technological newcomers and shuts them down before they spread. Maybe by some natural process we do not yet understand. Maybe by the simple fact that any civilization advanced enough to launch von Neumann probes is also advanced enough to realize doing so is dangerous. Whatever the answer, the absence of probes is a piece of evidence as loud as any signal we have ever failed to find. It tells us that something, either nature or other minds, or our own assumptions about technology, is keeping the galaxy clean of expanding machines. A clean galaxy, after 13 billion years, is the most unnatural thing the temporal Fermi paradox predicts. It should not look like this. It should be crawling. The fact that it is not means something has been actively preventing it. What that something is, we do not know. And that not knowing is a problem with no comfortable answer. In 2017, a physicist named Anders Sandberg, working with two colleagues at Oxford, proposed an idea that shocked even the people who study deep cosmic questions for a living. They called it the aestivation hypothesis, and it offers a haunting answer to where everyone has gone. The word aestivation means a long period of dormancy, like hibernation but for hot conditions. The idea is borrowed from biology. Some animals sleep through summer the way others sleep through winter. The Oxford team applied this concept to civilizations. Their argument starts with a quirk of physics. Computing, at the deepest level, has a thermodynamic cost. Every calculation generates a small amount of heat. The colder the environment, the cheaper the calculation. If you are an advanced civilization that has converted itself into computational beings, perhaps minds running on vast machines, the temperature of the universe matters enormously to you. Right now, the universe is too warm. That sounds strange given the freezing void of space. But the cosmic background radiation, the leftover heat from the Big Bang, is currently around -450 degrees Fahrenheit. That is not cold by computational standards. As the universe expands and cools over the next trillions of years, that background temperature will keep dropping. Eventually, it will approach absolute zero. A civilization that wants to do the maximum amount of thinking with the minimum amount of energy would benefit enormously from waiting. Every degree the universe cools makes their future computations dramatically more efficient. The math suggests that aestivating until the universe approaches its coldest possible state could allow a civilization to do something like 10 to the 30 power times more thinking than they could do today. If you are an old civilization, that ratio is not a small bonus. It is the difference between living a short, expensive life now and living an enormous, cheap life later. The smart move, if you can afford it, is to sleep. So the aestivation hypothesis suggests that the older, wiser civilizations of the galaxy may have already shut themselves down, not because they died, not because they collapsed, because they made the calculation and chose dormancy. Their machines are still out there, somewhere, in cold storage. Their minds are paused. They will wake up when the universe is finally cool enough to think the way they want to think. If true, this changes everything. The galaxy is not empty because civilizations are rare. It is empty because most of the great civilizations have already gone to sleep, and they are guarding their resources for a future trillions of years from now. They do not broadcast. They do not expand. They do not interact. They wait. This also implies they would not appreciate anyone making noise nearby. A young civilization stomping around, making radio broadcasts, and burning energy is, from their perspective, polluting their long quiet. The aestivation hypothesis quietly suggests that contact with newcomers, like us, would not be a celebration. It would be an annoyance, to be silenced. And there is a more disturbing layer. If the older civilizations are sleeping but have set up automated defenses or watchers to protect their hibernation, then the silence we hear could be enforced. Anyone who tries to make a galactic-scale noise might find themselves quietly turned off, not as a punishment, just as housekeeping. The galaxy as a quiet sleeping body, full of waiting minds we cannot wake up safely, is one of the strangest answers to the Fermi paradox ever proposed. It also fits the data better than most. The sky is empty because the dreamers have not yet decided to dream. And if we are loud enough, we might find out who is sleeping next door. Evolution does not aim at intelligence. It aims at survival. For most of Earth's history, the two have had very little to do with each other. The dinosaurs ruled this planet for 175 million years. They had brains the size of walnuts. They never built a city, never lit a fire, never sent a signal. By every meaningful measure, they were spectacularly successful. They dominated land, sea, and air. They survived multiple climate shifts. They outlasted entire continents. Then a rock hit the Yucatan Peninsula and ended them in an afternoon. Mammals, the survivors, took over. For 66 million years, mammals diversified. Most of them got by just fine, without big brains. Mice are smart enough to be mice. Cows are smart enough to be cows. Whales have huge brains but never built a single tool. Across millions of mammal species, over tens of millions of years, exactly one branch developed the kind of intelligence that builds technology. That branch is us, and we have only had it for about 300,000 years. This is the uncomfortable truth at the center of the temporal Fermi paradox. Intelligence may not be a destination evolution naturally arrives at. It may be a glitch, a rare, accidental configuration of neurons that happened once on this planet and has not happened again, even though the planet has had billions of years and millions of species to try. If intelligence is a glitch on Earth, it may be a glitch everywhere, which means the rare moments when it appears are exactly that: brief, accidental, possibly self-extinguishing. Consider what big brains actually cost a species. Human brains use about 20% of our total energy intake, despite being only 2% of our body weight. Pregnancy is dangerous because human babies have heads too big for easy birth. Childhood lasts longer in humans than in almost any other species, requiring years of care before the young can survive on their own. Big brains demand enormous calories, complex social structures, and long developmental periods. This is a heavy evolutionary tax. In most environments, paying it does not make sense. A species with a smaller brain, faster reproduction, and simpler needs almost always outcompetes a smarter rival. Intelligence is a luxury that only a few species, in very specific conditions, can afford. Now apply this across the galaxy. If only a tiny fraction of life-bearing planets ever produces a species capable of paying the intelligence tax, And if those species only stay technological for a brief window before something stops them, the result is exactly the silence we hear. The window is so narrow that it does not just limit alien civilizations, it threatens our own. Humans have been technological for about 250 years. We have nuclear weapons that can wipe us out in an afternoon. We have changed our climate in ways we are still learning to measure. We have built systems so complex that no single person fully understands them. The very intelligence that got us here is creating problems we may not be smart enough to solve. If intelligence is a glitch, then the glitch eventually corrects itself. Either the species figures out how to manage its own power without destroying itself, or the glitch ends, the window closes. The species either evolves past the dangerous phase or does not survive it. The galaxy may be full of planets that produced this glitch and lost it. Each one had its moment of awareness. Each one looked up at the stars, asked where everyone else was, and got no answer. Each one made the same mistakes that brief, intelligent species tend to make. We are running the experiment right now. The result of every previous run, as far as we can tell, was silence. That is not encouragement. That is a warning written in the absence of every other voice. Earth has had 5 major extinction events in the past 500 million years. Each one wiped out most of the species alive at the time. Each one left a chemical signature in the rock layers, a fingerprint of mass death. If a paleontologist from another planet ever visited Earth, they could read those layers. They would see the iridium spike from the asteroid that killed the dinosaurs. They would see the sulfur and carbon shifts from the great volcanic events. They would see the patterns of life rising, peaking, and being cut down, written in stone over geological time. Now turn that idea around. What would Earth's fingerprints look like to someone scanning from far away? And what fingerprints might other dead worlds be sending us right now without us knowing how to read them? This is one of the youngest fields in astronomy. Some scientists have started calling it astropaleontology, though the field has no official name yet. The idea is to look for the chemical evidence of life and possibly civilization on planets that no longer support either. The signs of past life on a planet do not vanish quickly. Oxygen in an atmosphere is one of the strongest hints. Earth's atmosphere is more than 20% oxygen, and that level only exists because plants and certain bacteria pump oxygen out as a byproduct of photosynthesis. Without ongoing biological activity, oxygen would react with rocks and water and disappear in a few million years. So if a planet has high oxygen, something is making it right now. A planet that used to have life but lost it might still show traces. Methane in unusual quantities, carbon isotope ratios that look biological, surface coloration that hints at chlorophyll-like compounds. These signatures decay, but slowly. A world that died 1 million years ago might still look biologically active to a distant observer. A world that died 100 million years ago might show only faint hints. A world that died 1 billion years ago might look completely dead. Some astronomers wonder if planets in our local stellar neighborhood already show this kind of decay. There are stars within a few hundred light years of Earth that are older than our Sun, and some of those stars have rocky planets in their habitable zones. A few of those planets show atmospheric chemistry that does not quite match what natural geology should produce. The standard interpretation is that we are seeing weird natural processes we do not yet understand. The temporal Fermi paradox suggests another reading. We may be looking at the chemical bones of dead biospheres, worlds that hosted life for billions of years and then lost it, leaving behind atmospheres that are slowly returning to lifeless equilibrium. If a civilization existed on one of those planets, the signs would be even subtler. Industrial activity leaves chemical fingerprints. Artificial gases, like chlorofluorocarbons, do not occur naturally. Heavy isotopes of certain elements get concentrated by industry. A civilization that lasted 1 million years would have saturated its planet with these markers. Even after the civilization ended, the markers would persist in trace amounts for tens or hundreds of millions of years before fully decaying. This means there is a window, somewhere between 1,000,000 and 1,000,000,000 years after a civilization dies, during which their fingerprints are still detectable to a careful observer. Outside that window, the planet looks completely natural again. We are looking at the galaxy with telescopes that can, for the first time, actually pick up these fingerprints. The James Webb Space Telescope, launched in 2021, is capable of analyzing the atmospheric chemistry of planets light years away. It is building a catalogue. Most of the planets it studies look natural. A few have shown anomalies that scientists are still trying to explain. Somewhere in that catalogue, there may be a world that died long before humans evolved. The signal of its death is faint, ancient, and easy to miss. But it is there, written in the gases of its sky. We just have to learn how to read tombstones we did not know existed. The Sun is about 4.5 billion years old. That sounds ancient. By human standards, it is unimaginably old. By cosmic standards, it is middle-aged at best. Most of the stars in the galaxy are older than the Sunday. Astronomers estimate that about 70% of the stars in the Milky Way formed before our Sun did. Some of them are 9, 10, even 12 billion years old. They have been burning since long before Earth existed. They have hosted planetary systems for stretches of time longer than our entire planetary history. This fact alone is enough to break the standard picture of the Fermi paradox. We tend to think of life as a competition that started at roughly the same time everywhere. The truth is that life had a head start in most places. By the time Earth formed, the galaxy was already old. Trillions of opportunities for life had already come and gone. Consider what those opportunities looked like. A star that is 8 billion years old and similar in size to our Sun has been stable for far longer than the entire history of life on Earth. If that star had a rocky planet in its habitable zone, that planet could have hosted life for nearly twice the time Earth has hosted life. Twice the time means twice the chances for evolution to produce something complex. Twice the chances for that complex something to develop intelligence. Twice the chances for that intelligence to build technology. And then twice the chances for the technology to fail and disappear. This is the key point. An older star system is not just a system where life had more time to evolve. It is a system where life had more time to come and go. A planet that began producing complex life 8 billion years ago could have already gone through multiple cycles of biological diversification, possibly multiple intelligent species, and possibly multiple technological civilizations. Each one would have risen, expanded, and ended. Each one would have left its own thin layer of fossils. By the time we look at that system today, the star itself may be entering its old age. Stars get more luminous as they age, especially as they approach the end of their main sequence phase. The habitable zone shifts outward. Inner planets that were once temperate get scorched. Outer planets that were once frozen warm up. The whole system reshapes itself, and any biosphere that did not adapt fast enough gets cooked off. There are stars in our local galactic neighborhood that have already begun this shift. Their inner planets are dead worlds, with thin atmospheres and surfaces that look like glass. Their outer planets are warming up but still hostile. Anyone who lived there is gone. This is what some astronomers call the habitability sweep. It is a slow-motion erasure of biospheres as their parent stars age. Over the lifetime of a galaxy, the sweep moves through every star system, eventually wiping out whatever life existed inside it. For our search for intelligent life, this means a lot of the most promising star systems in the galaxy are already past their prime. The civilizations they may have hosted have been extinct for millions or billions of years. The planets are scorched. The biological clocks have run out. Our Sun is unusual in that it is still in the middle of its stable phase. Earth still has hundreds of millions of years before our star's increasing brightness makes the planet uninhabitable. We are living during one of the rare, quiet windows in our system's history. Most of the older systems in the galaxy are past that window. Most of the younger systems have not reached it yet. In that sense, We are not just searching across space, we are searching across timing windows, and most of the windows have already closed. In 1996, an economist named Robin Hanson proposed a deceptively simple idea. He called it the Great Filter, and it has become one of the most discussed concepts in the search for extraterrestrial intelligence. The Great Filter argues that somewhere along the path from dead matter to galaxy-spanning civilization, there is at least one barrier so difficult that almost nothing gets past it. The filter is what explains the silence. Whatever it is the reason the galaxy is not already filled with thinking life. The terrifying question is where the filter sits. There are roughly 9 major steps a planet has to climb to produce an interstellar civilization. The right kind of star, the right kind of planet, stable conditions for billions of years, the emergence of self-replicating chemistry, the leap from simple to complex cells, the development of multicellular life, the evolution of intelligence, the development of technology, the successful expansion into space. The Great Filter could be any one of these steps. It could be several. It could be a step we have not yet identified. Here is what makes the question so urgent. If the filter is behind us, we have already passed it. The hardest barrier is in our past, and the silence of the galaxy reflects the fact that almost no other planet got this far. We are the lucky ones, the rare exception, the survivors of a brutal cosmic selection. If the filter is ahead of us, we are walking toward it. Some scientists argue the filter is most likely behind us. They point to specific steps that may be wildly improbable. The leap from simple bacterial cells to complex eukaryotic cells, for example, only happened once in Earth's history, more than 2 billion years ago. Every plant, animal, and fungus on Earth descends from that single event. If that step is the filter, then most planets in the galaxy stop at the bacterial stage and never go further. The reason the sky is silent is that we are nearly alone. Others argue the filter is ahead. They point to a different kind of evidence. If intelligent species developing technology were the filter, we would expect to see most of those species end up self-destructing. The silence would then be the silence of failed civilizations. Each one rose, became technological, hit some catastrophic barrier, and ended. The difference between these two views is everything. If the filter is behind us, we are special, but the universe is hostile to life in general. Future humanity has a real chance of expanding into the galaxy and finding it empty, ready for occupation. If the filter is ahead of us, we are not special. Many civilizations got this far. Most of them died. Whatever killed them is waiting for us. It might be nuclear war. It might be runaway artificial intelligence. It might be biological weapons or environmental collapse, or something we have not yet thought of. Whatever it is, the data of cosmic silence suggests it works. It works almost every time. There is a sobering reason to think the filter may be ahead. If it were behind, we would expect to find no evidence of life elsewhere. If it is ahead, we might find evidence of past civilizations everywhere, planets where life evolved, civilizations that rose, technologies that flourished, and then everything ended. Every time scientists discover that life is more common than we thought, that filter shifts forward in time. Every time we find evidence of ancient water on Mars, or organic compounds in meteorites, or planets with atmospheres similar to Earth's, the case for a filter behind us gets weaker, the case for a filter ahead gets stronger. We may be reading our own future every time we discover signs that we are not the first. The silence is not just a question, it is a clock. Searching for alien life is hard. Searching for alien life that is no longer alive is much harder. When astronomers point their instruments at the sky looking for civilizations, they are mostly looking for signals, radio waves, laser pulses, the infrared glow of energy-harvesting megastructures. All of these assume the civilization is active. The signal they leave depends on them still being there to send it. What if the civilization is gone? A dead civilization does not broadcast. It does not build. It does not maintain. Whatever evidence it left behind starts the moment the broadcasters die, and that evidence begins decaying immediately. This is the new problem the temporal Fermi paradox asks us to solve. How do you detect something that has already ended? The answer requires shifting from listening to digging, from astronomy to something closer to archaeology, scaled up to a galactic level. Some markers last longer than others. A planet that once hosted a civilization might still show isotopic anomalies in its atmosphere. Heavy industry leaves chemical fingerprints, including unusual concentrations of certain isotopes that natural geology rarely produces. These fingerprints fade over millions of years, but slowly. A civilization that died 100 million years ago might still be detectable to an extremely sensitive instrument, if you know what to look for. Surface features can also persist. Massive mining operations, large artificial lakes, geometric patterns from agriculture or city building, all of these create disturbances in the natural landscape that can survive for tens of millions of years before erosion erases them. The right space telescope, with enough resolution, could potentially spot the ghost of an ancient civilization on a planet's surface. Larger structures last even longer. A Dyson swarm built to last would leave debris in orbit around its star for hundreds of millions of years. The dust cloud would slowly spread, but the heat signature, the unusual orbital patterns, and the chemical composition of the debris would still hint at engineering. There are even more exotic possibilities. Some scientists have proposed that an extremely advanced civilization might leave deliberate markers designed to last across deep time. Lunar surfaces, asteroid compositions, or the orbital arrangements of moons could be modified to encode information that would survive for billions of years. We do not know what such markers would look like. We do not even know how to look for them. But the concept is real, and it changes the search dramatically. Imagine if the moons of Jupiter were arranged in a pattern that matched a mathematical sequence too precise to be natural. Or if the surface composition of a particular asteroid showed elemental ratios that could only result from deliberate sorting. These would be ancient messages, left by something long gone, waiting for the next intelligent species to grow up enough to notice. Some researchers have started checking. They have looked at the orbital resonances of moons around the gas giants, the chemistry of unusual asteroids, and the strange variability of certain stars. So far, nothing definitive. But the search is barely beginning, and the data is enormous. There is a deeper problem with searching for dead civilizations. We do not know how dead civilizations behave. We assume they leave evidence we can recognize. But a civilization advanced enough to last millions of years and then end might also have been advanced enough to clean up after itself, or to transform its remnants into something we cannot distinguish from natural processes. A truly old civilization might be invisible by design. Their goal might have been to leave behind nothing, or to leave behind something so subtle that only another civilization at the same level could detect it. We may be standing in a galaxy filled with archaeological sites, walking past them every night, mistaking ancient ruins for ordinary stars. The bones are out there. We just have not learned to dig. Imagine an alien archaeologist visiting Earth 100 million years from now. Humans are gone. Our cities have crumbled. The continents have shifted. The oceans have moved. The fossil record of our existence has been compressed into a thin layer of plastic, concrete fragments, and unusual isotopes scattered across the geological strata. That alien archaeologist would have a hard time proving humans existed. Most of what we built would be erased. The Great Pyramids would be eroded to dust. Mount Rushmore would be unrecognizable. New York would be buried under sediment or melted into glass. What would survive? Probably the strangest leftover would be a thin chemical signature. Plastics break down slowly, leaving microscopic markers in soil. Radioactive isotopes from nuclear testing in the mid-20th century would still be detectable, if barely. The isotopic ratios of carbon in Earth's atmosphere would show a sudden shift starting in the 1800s, when humans began burning fossil fuels at industrial scale. These chemical fingerprints, faint but unique, would be the most reliable evidence that something intelligent had once lived here. Buildings, vehicles, and infrastructure would not last. A skyscraper, abandoned and exposed to weather, collapses within a few hundred years. A concrete dam erodes within a few thousand. Even bedrock-anchored structures get crushed by glacial cycles, earthquakes, and the slow grinding of geological time. 100 million years from now, there would be no Statue of Liberty. There would be no surviving books, no surviving art, no surviving cities. There would be a chemical whisper in the rocks, and that is all. Now, scale this up. Earth is one planet. What if a civilization existed on a planet 1,000 light years away and ended 100 million years ago? Every clue to their existence would have undergone the same kind of erasure. Their cities would be dust. Their satellites would have decayed. Their atmospheric chemistry would be slowly returning to baseline. To us, watching from across 1,000 light years, that planet would look ordinary, just another rocky world, orbiting just another star. The chemical whispers, if they survived, would be too faint to detect with current technology. The orbital debris, if any was left, would look like normal asteroid fragments. This is the silent reality of the temporal Fermi paradox. The galaxy might be filled with ruins, not the dramatic ruins of science fiction, with broken statues and crumbling spires. Real ruins, geological ones, chemical ones, the kind that look like nothing unless you know what you are looking for. There may be hundreds of dead worlds in our local galactic neighborhood, each one a graveyard of intelligence that ran its course and ended, each one indistinguishable from our distance, from a sterile rock that never produced anything at all. We would have no way of knowing the difference. This is why some scientists have started arguing for a new kind of search, not just listening for signals, but looking for chemical anomalies. Atmospheres that contain industrial gases, surfaces with unusual heat distributions, orbital patterns that suggest engineering. The data is mostly still out of reach. Our telescopes are getting better, but they are still nowhere near sensitive enough to read the chemical fingerprints of dead civilizations across hundreds of light years. The James Webb Space Telescope can detect basic atmospheric composition on a handful of nearby exoplanets. Future telescopes will do more. None of them, yet, can read the ghosts of industrial activity from the distant past. We are walking through a museum where most of the exhibits have been worn down to dust. The dust is still there, scattered across the rocks. Some of it carries information. Most of that information is just below our threshold of detection. The ruins are out there. We are too primitive to read them. That is going to change. The question is whether we will read them before our own ruins join the catalogue. In 1961, astronomer Frank Drake sat in front of a chalkboard and wrote down a formula. He was trying to estimate the number of detectable civilizations in the Milky Way. The result has been argued about ever since, and the formula, now called the Drake equation, has become one of the most famous tools in the search for alien life. The original equation looks like this. Start with the rate of star formation in the galaxy. Multiply by the fraction of stars with planets. Multiply by the fraction of those planets that could support life. Multiply by the fraction that actually develops life. Multiply by the fraction where intelligence arises. Multiply by the fraction where intelligent species develop communication technology. Finally, multiply by the average length of time a civilization stays detectable. That last variable is the trap. For decades, scientists plugged numbers into the Drake equation and got wildly different answers depending on how optimistic or pessimistic they were. Some came up with millions of civilizations in the galaxy. Others came up with a fraction of one, suggesting humanity might be alone. The disagreement always came back to the last variable. How long does a civilization broadcast? What the original equation underweights is how synchronization works. Even if the equation predicts 1,000 civilizations have existed in the galaxy across its history, that does not mean 1,000 are out there now. It means 1,000 exist when you sum across all of cosmic time. At any given snapshot, the number alive and broadcasting may be much smaller, possibly zero. The fix is simple in concept and brutal in implication. You add a temporal density factor. Take the total number of civilizations, divide by the age of the galaxy, and multiply by the typical broadcast lifetime. That gives you the expected number alive and detectable at any single moment. Run the math with reasonable assumptions. Suppose civilizations broadcast for an average of 500 years before either going silent or ending. Suppose 1,000 civilizations have arisen across the last 10 billion years of galactic history. The expected number broadcasting at any single moment becomes the 1,000 multiplied by 500 divided by 10 billion. That equals 0.000005, effectively zero. Even a galaxy with 1,000 intelligent civilizations across cosmic history might have zero broadcasting at any given moment. This is what the original Drake equation hides. It calculates a theoretical maximum without accounting for the fact that civilizations are spread across time, not just space. A galaxy could be successful at producing intelligence and still appear silent at every snapshot. Researchers who study this version of the equation have started calling the new variable the synchronization factor. It captures how often two civilizations exist at the same time, in the same observable region, with overlapping broadcast windows. The synchronization factor is brutal because it depends on broadcast lifetime, and broadcast lifetimes are short. Humans have broadcast for 130 years. If we last another 500, we will have been a brief flash. Multiply that by the millions of years between civilizations, and the chance of overlap collapses. The implications cut both ways. They suggest the Fermi paradox may not require any exotic explanation at all. No great filter, no Grabby aliens, no deliberate silence, just statistics. Just the brutal arithmetic of brief lives spread across deep time. They also suggest something darker. If synchronization is the bottleneck, then no amount of better telescopes, faster probes, or more sensitive radio receivers will solve the problem. The problem is built into time itself. We can build the best instruments imaginable and still hear nothing because the voices we are listening for went quiet long ago. The Drake equation gave us hope by suggesting the math was favorable. The temporal version takes that hope and reorganizes it. There may have been many voices. There may yet be many more. We are just listening at the wrong moment, and our own broadcast window is still ticking down. Not every civilization has to die to disappear. Some may have simply stopped being detectable. This is one of the more unsettling possibilities in the modern Fermi paradox debate. It suggests that civilizations advanced enough to last a long time may eventually move beyond the kind of activity we know how to look for. They do not collapse. They do not get destroyed. They transition into something else, something quieter, and we cannot see them anymore. Consider where humans are headed. Right now, we transmit huge amounts of information through the air. Radio, television, satellite communications, cellular networks. All of these leak energy into space, even when they are not aimed there. That leakage is what makes us detectable to anyone listening from another star system. The leakage is shrinking. Modern communication increasingly uses fiber optics, which sends light through cables and leaks almost nothing. Cellular networks use tighter beams aimed at specific antennas. Satellite communication uses focused beams pointed at specific receivers. Quantum communication, still in its infancy, may someday allow information transfer with zero electromagnetic leakage at all. If this trend continues, Earth will eventually go quiet. Not because civilization ended, but because we became efficient. Our radio bubble will stop expanding. The existing bubble will continue outward, fading as it goes, and eventually we will become invisible to the kind of search we currently use to look for others. A civilization 1,000 years more advanced than ours has probably already finished this transition. They are not broadcasting, they are not leaking. Their communication is so tight, so efficient, so contained that no detectable energy escapes their planet. From our perspective, they are silent. From their perspective, they are simply having a normal conversation we cannot eavesdrop on. Now extend the logic further. A civilization 1,000,000 years more advanced has probably moved beyond electromagnetic communication entirely. They may use gravitational waves, neutrino streams, or methods we have not yet imagined. Their planets, if they still live on planets, would show no obvious signs of technological activity. Their stars might still have natural-looking spectra. Their ships, if they have ships, might travel through means that leave no traceable energy signatures. Some scientists go further. They argue that very advanced civilizations may eventually upload themselves into computational substrates, not bodies on planets, but minds running on machines. Those machines might be small, dense, and hidden. They might be inside asteroids. They might be deep in the cores of moons. They might be embedded in the dust clouds of nebulae, where natural radiation makes detecting artificial activity nearly impossible. A galaxy full of uploaded minds would look completely empty to a civilization at our level. The minds would not need radio. They would not need light. They would not need the surface of a planet. They would exist in pockets of dense computation, invisible to telescopes, indifferent to anyone outside their substrate. This idea, sometimes called the transcension hypothesis, suggests that the silence is not about civilizations ending. It is about civilizations evolving past the point where we can perceive them. They are still here, they are still active, they are just no longer in our category of observable phenomena. There is something dark about this possibility. It implies that the path of intelligence eventually leads away from the physical universe as we understand it. Civilizations grow up, become powerful, and then withdraw. They turn inward. They build their own private worlds inside computational substrates and lose interest in the messy, energy-expensive business of physical existence. If that is true, then humanity is just a species that has not yet made the transition. We are loud, we are leaky, we are visible. The advanced civilizations are not. They left the stage long before we arrived, and they are watching, if they bother to watch at all, from places we cannot see. The galaxy may not be empty. It may be hidden in plain sight. There is no single time in the galaxy. Every observer has their own. This is one of the strangest things about studying cosmic history. Time is not a universal quantity. It depends on where you are, how fast you are moving, and how strong the gravity is in your local region. A clock on Earth ticks at one rate. A clock on a planet near the galactic center, where stars are denser and gravity is stronger, ticks slightly slower. A clock on a fast-moving probe, traveling at a significant fraction of the speed of light, ticks much slower than either. For ordinary life, this barely matters. The differences are tiny over short distances and short times, but scale up to galactic distances and billions of years, and the clock differences become real. A signal sent from one part of the galaxy to another does not just travel through space, it travels through different time references. By the time it arrives, the clocks at the destination have ticked at a slightly different rate than the clocks at the origin. The signal carries timestamps that may be off by years or even centuries depending on the gravitational and motional differences between the two locations. This becomes a problem when you try to coordinate civilizations. Imagine two intelligent species trying to plan a meeting. One lives near the galactic core, where time runs slower. The other lives in the outer galactic disk, where time runs slightly faster. They send messages back and forth, but each message takes thousands of years to travel between them. By the time they agree on a meeting date, the date itself is ambiguous. Whose clock are they using? When the meeting day arrives, are they both there at the same moment, or has one of them already arrived and left? The problem gets worse when you account for the fact that civilizations themselves have lifespans. If a civilization lasts 100,000 years and is trying to coordinate with another civilization 100,000 light years away, the messages will take longer to arrive than the entire lifespan of the senders. By the time the response comes back, the original civilization is gone. This is sometimes called the galactic clock problem, and it makes interstellar civilization, in any meaningful sense, almost impossible. Any species that wants to operate across galactic distances has to either find a way to live for millions of years or accept that their communication is one way. Messages out, no replies expected. This may explain why we do not see signs of organized galactic civilization. The math may not support it. Even an extremely advanced species, capable of building probes and broadcasting across the galaxy, may have given up on coordination because the timing problems are unsolvable. They send messages into the dark, not expecting answers. They build and broadcast and explore individually, without ever forming alliances or empires that span the galaxy. The result, from an outside observer's perspective, is silence. Not because civilizations are absent, but because they cannot synchronize. Each one operates in its own local time bubble, with its own local concerns, unable to participate in any kind of larger conversation. There is something poetic about this. The galaxy is too big for civilizations to know each other. The time differences are too severe for coordination. The distances are too vast for real-time interaction. Any species capable of spanning the galaxy must accept that they will be alone in any meaningful sense, even if they manage to detect signs of others. Perhaps every species reaches this realization eventually. Perhaps the silence we hear is the silence of civilizations that figured out the math, decided that interstellar conversation is impossible, and stopped trying. They are not hiding. They are not gone. They are just busy with their own corners of the clock, where time still makes sense, and where the noise of the wider galaxy is too distant and too out of sync to bother chasing. We may be at the same threshold ourselves. Once we realize the galaxy cannot be coordinated, what would we do differently? Would we keep broadcasting? Or would we settle into our own quiet bubble, content with our own clock, and let the rest of the galaxy go its separate way? The search for extraterrestrial intelligence, known as SETI, began in 1960 when astronomer Frank Drake pointed a radio telescope at two nearby sun-like stars and listened for signals. He heard nothing. 65 years later, despite countless improvements in technology, sensitivity, and computing power, SETI has still heard nothing. The standard interpretation is that aliens are rare, distant, or hiding. The temporal Fermi paradox suggests a different, harder explanation. SETI has been built on an assumption that may have been wrong from the very first day. The assumption is contemporaneity. SETI assumes that the signals it is looking for are coming from civilizations alive right now, broadcasting right now, in a way we can detect right now. That assumption is everywhere in the search. The frequencies SETI listens to are chosen because they are the frequencies a civilization at our level would likely use. The patterns it looks for are patterns a present-day civilization would create. The data analysis filters out anything too old, too faded, or too unusual to fit the model of a modern broadcast. The result is that SETI is optimized to find civilizations almost exactly like ours, broadcasting almost exactly the way we broadcast, in roughly the same era we are listening. That is a vanishingly narrow target. If the temporal Fermi paradox is right, that target may be empty by definition. Consider what SETI cannot detect. It cannot detect signals that have already passed. Any broadcast that washed past Earth before 1960 is gone. The signal continued onward, into the deeper galaxy, but Earth missed it. We were not listening. We did not have the technology. We did not exist as a radio civilization yet. It cannot detect signals from civilizations that broadcast on different frequencies. SETI focuses on a relatively narrow band of the electromagnetic spectrum, partly because of physics and partly because of practical constraints. A civilization that uses laser pulses, neutrino beams, or methods we have not invented yet would be invisible to traditional SETI searches. It cannot detect signals from civilizations that have moved beyond broadcasting. As discussed earlier, an advanced civilization may have stopped leaking electromagnetic energy entirely. If they exist now but communicate through tight beam fiber optics or quantum methods, SETI hears silence even though they are right there. It cannot detect the dead. A civilization that ended 1,000,000 years ago is silent now. Their signals have either dispersed past detectability or moved on past Earth. SETI has no way to know they ever existed unless their signals happen to be passing through right now. In other words, SETI listens for a very specific kind of neighbor, a neighbor at our technological level, a neighbor broadcasting at our frequencies, a neighbor alive at our time, a neighbor who has decided to be loud. The galaxy may not have produced many of those neighbors. The galaxy may have produced thousands of civilizations, none of which match that profile. SETI's silence, in this view, is not evidence of absence. It is evidence of mismatch. There are scientists who have started arguing for what they call the search for extraterrestrial archaeology. Instead of listening for live signals, they want to look for signs of past civilizations, atmospheric chemistry, stellar dimming patterns, unusual orbital arrangements, things that would persist even after a civilization is gone. This kind of search is harder than SETI. It requires more sensitive instruments, more sophisticated data analysis, and a willingness to look for things that may not exist in the form we expect. But it has the advantage of casting a wider net across time. A successful detection might find a civilization that has been gone for 100 million years instead of requiring one that is alive and broadcasting today. The shift is slow. Most of the budget and attention is still going to traditional SETI. The temporal Fermi paradox suggests this may be a mistake. We are looking for live voices when the galaxy may only contain echoes, and we have not yet built the equipment to detect echoes from deep time. The voices are not necessarily gone. We are listening with the wrong ears. There is a phrase astronomers use sometimes, half as a joke and half as a warning. They call Earth a young planet around a young star in a young patch of the galaxy. The phrase sounds reassuring at first. Youth implies a future. Youth implies time ahead. But the more you think about it, the heavier it becomes. Earth formed about 4.5 billion years ago. The Sun is roughly the same age. We orbit a fairly average star in a fairly average part of the Milky Way's disk, several thousand light-years from any region with unusual stellar density or activity. By every measure, we live in a calm, uneventful, mostly empty corner of the galaxy. This sounds like a good thing. Calm corners are safe corners. No supernovae nearby. No high radiation zones. No gravitational disturbances ripping our solar system apart. Earth has been allowed to develop life over billions of years, partly because nothing has interrupted us. The cost of that calm is loneliness. The most active regions of the galaxy, the dense clusters, and the inner regions near the galactic core are also the most chaotic. Stars are packed close together. Supernovae are common. Radiation is intense. Most life that tries to develop in those regions probably gets sterilized before it can advance very far. But the calm regions, like ours, have a different problem. Stars are far apart. Civilizations, if they arise, are isolated by enormous distances. There are fewer chances for accidental contact, fewer opportunities for interstellar interaction, fewer reasons for messages to overlap. Earth sits in one of the calmest, quietest, most isolated parts of the galaxy. We are far from any region where life might be common. We are far from any region where signals might cluster. We are far from anywhere a passing alien civilization might want to visit. Our calm is also our solitude. Now add the time dimension. The Sun is younger than 70% of the stars in the galaxy. That means most stars older than ours have had their planetary systems for longer than ours has existed. If life is common, most of it had a head start measured in billions of years. But here is the twist. The older stars are concentrated in certain regions. The galactic bulge, near the center, is full of ancient stars. The galactic halo, far above and below the main disk, is also old. Our region, the thin disk where the Sun lives, is full of younger stars. The stars near us are mostly close to our age or younger. This means even if life had a head start somewhere in the galaxy, it had it far from us. The civilizations that may have risen and fallen during the past 10 billion years probably did so in regions distant from our local neighborhood. Their signals, if any reached this far, would have been so attenuated by distance that we could not detect them. Their probes, if any came this way, might never have made it. We are not just isolated by the present, we are isolated by the geography of time. The action, if there ever was any, happened far away and long ago. This is the lonely young Earth, a planet that is young in cosmic terms, orbiting a young star in a young region of a galaxy that is mostly old. We are a baby surrounded by ghosts. The neighborhood was built and abandoned before we moved in, and the next neighbors are hundreds of millions of years away from arriving. The math suggests we should be alone, and the math is not optimistic about whether that will change. Even if intelligent life is common, the odds that another civilization rises in our local region during our brief window of detectability in a way that overlaps with us are small enough to be statistically zero. We are not the center of a busy galaxy. We are one quiet voice in a calm, empty corner, calling out to a sky that has long since gone to sleep. There is a specific kind of signal worth thinking about carefully. Not a live broadcast, not a deliberate message aimed at Earth, but an echo. A signal sent so long ago that its source has been gone for 100 million years, still traveling through space, still passing through our solar system, still potentially detectable if we knew how to look. These echoes are, in theory, the most common kind of alien signal we could ever encounter. Live broadcasts from current civilizations are rare because civilizations are rare, brief, and out of sync. Echoes from past civilizations are everywhere, scattered across the galaxy, washing through every star system as their wavefronts expand outward across cosmic time. The problem is that echoes are weak. A signal sent from a civilization 1,000 light years away takes 1,000 years to reach us. By that point, the energy of the original broadcast has spread over a sphere with a radius of 1,000 light years. The signal hitting Earth is a tiny fraction of what was sent. Detect it requires extraordinary sensitivity. Now imagine a signal sent from 10,000 light years away. It has spread over 10 times the radius. Its strength at Earth is 100 times weaker than the 1,000 light-year signal, just from geometry alone, before you account for any other losses. Push it to 100,000 light-years, the diameter of the galaxy, and the signal is 10,000 times weaker still. By that point, even an originally powerful broadcast becomes nearly indistinguishable from background noise. Push it further, into deep time. A signal sent 1 million years ago has been traveling for 1 million years. Its current location is a thin shell about 1 million light-years thick, spreading outward. Most of that shell is in the empty space between galaxies, where no one is listening. A small portion is passing through stars and planets, but the energy density at any single point is so low that detecting it requires equipment far beyond what we currently have. This is why echoes are so frustrating. They are theoretically there. They might even outnumber every other type of signal in the galaxy, but they are below our detection threshold, and they will likely remain below our detection threshold for a long time. Some scientists have proposed that the signals we should look for are not the original broadcasts, but the reflections. When a signal hits a planet, a star, or a dust cloud, some of it bounces back. Those reflections are weaker than the original, but they create a faint, complex pattern in the cosmic noise. With enough sensitivity and the right algorithms, it might be possible to detect the existence of an ancient signal by studying the patterns of its echoes off natural objects in the galaxy. This is theoretical. No one has done it successfully, but the idea changes the search. Instead of listening for direct messages, you listen for the way the galaxy itself responds to messages that passed through long ago. The galaxy becomes the receiver, and we become eavesdroppers on a conversation it had with itself in the distant past. There is something poetic and disturbing about this idea. It suggests that the most reliable way to find ancient civilizations is to study how their broadcasts shaped the natural environment around them. Civilizations leave fingerprints on space itself. The fingerprints are subtle, faint, and slowly fading, but they are real. The next generation of radio telescopes, including planned arrays in space and on the far side of the moon, may begin to catch these faint patterns. The Square Kilometre array, currently under construction, will be sensitive enough to detect signals far weaker than anything our current instruments can pick up. It may begin to hear the cosmic background hum more clearly than ever before. Inside that hum, somewhere, there may be patterns left by ancient transmitters, or there may be nothing. The galaxy may have been quiet, not just to our ears, but to its own. If the echoes are there, we will find them. If they are not, we will know that the temporal Fermi paradox is even darker than we thought. The silence will mean that no one has been broadcasting for so long that even the echoes have decayed. A galaxy that quiet is not just empty, it is dead. A radio signal lasts as long as it can travel before fading into noise. A planet's atmosphere lasts as long as biological or geological processes maintain it. A civilization's machinery lasts as long as it is maintained, which means not very long once the civilization ends. But there is one kind of message that lasts almost forever, a message built into physics itself. This is one of the most exotic ideas in the search for extraterrestrial intelligence. Some scientists have proposed that an advanced civilization might leave messages encoded not in fading signals but in stable structures that survive across cosmic time. The arrangement of moons, the composition of asteroids, the orbital resonances of planets, the chemical patterns in stellar atmospheres, anything that natural processes alone would not produce. The idea is straightforward. If you want to send a message that lasts 1 billion years, you cannot use radio. You cannot use light. You cannot use any signal that decays. You have to use the universe itself. You have to arrange physical things in patterns that are stable, detectable, and impossible to explain through random chance. A civilization advanced enough to do this would have abilities far beyond ours, moving moons into specific resonance patterns, restructuring asteroid belts, building megastructures whose only purpose is to be noticed. We do not yet have the engineering capability to do any of this, but that is the point. A civilization 1 million years ahead of us might. Now, imagine they did, somewhere in our galaxy, hundreds of millions of years ago. Their engineering would have been carefully designed to last. Resonance patterns that survive gravitational drift, structures placed in stable orbits where they would not decay, compositions chosen for their longevity against cosmic radiation. Today, those structures might still be out there. The question is whether we would recognize them. Most natural systems in the galaxy follow predictable patterns. Stars distribute themselves in certain ways. Planets orbit in certain mathematical relationships. Asteroids cluster in certain belts and gaps. Astronomers have spent centuries learning what is normal. When something is not normal, they notice. The trouble is that most anomalies have natural explanations. An unusual orbital pattern might be the result of a recent gravitational disturbance. A strange stellar spectrum might be the result of unusual chemistry in the star's formation. An odd asteroid composition might be the result of a collision that scattered fragments from a larger body. Distinguishing between natural anomaly and engineered message is extraordinarily hard. You need to find something that cannot be explained by any natural process, no matter how unusual. You need to find a pattern so precise, so deliberate, that it could only come from intelligence. So far, no such pattern has been found. The galaxy looks natural in every way astronomers can measure. Either no one has left messages in physics, or the messages are subtle enough that we cannot tell them apart from cosmic randomness. There are a few candidates that have caught attention over the years. The unusual brightness variations of certain stars, the strange dust patterns around certain young systems, the odd orbital configurations of moons around the gas giants. None of these have turned out to be definitive. All of them have plausible natural explanations. But the search continues. As telescopes improve and data piles up, the parameter space for possible engineered messages narrows. Eventually, if such messages exist, we should find them, or we will find that the galaxy is genuinely natural. No deliberate fingerprints, no engineered patterns, no messages in physics. And that absence will tell us something. It will tell us that either no civilization ever reached the level of engineering required, or none of them ever decided to leave a record. Both options are unsettling. The first means the Great Filter is brutal enough to stop civilizations before they reach that level. The second means civilizations that reach that level choose not to leave traces, possibly because they have learned that being noticed is dangerous. The galaxy is a museum, or it is a graveyard. Either way, the exhibits are mostly invisible to us. We are still learning how to read the walls. The universe has not always been suitable for life, and it will not always be suitable for life. We exist during a brief, specific era when the conditions of the cosmos allow biology to function. Stars produce energy. Planets stay warm enough for liquid water. Heavy elements exist in sufficient quantities for complex chemistry. The temperature of the cosmic background radiation is low enough that thermodynamics works the way it does for us. This era will end. Stars do not last forever. The kinds of stars that produce light suitable for photosynthesis-based life. Stars like our Sun have lifespans measured in billions of years. Once they exhaust their hydrogen fuel, they expand, scorch their inner planets, and eventually collapse into white dwarfs that slowly cool over trillions of years. After that, they go dark. Smaller stars, called red dwarfs, last much longer. Some red dwarfs have lifespans of trillions of years, possibly tens of trillions. They burn so slowly that their fuel takes nearly forever to run out. As long as red dwarfs continue to burn, planets in their habitable zones can theoretically support life. But even red dwarfs eventually end. The longest-lived ones will exhaust their fuel sometime around 1 trillion years from now. After that, the universe will have no more main-sequence stars. The era of starlight will be over. What comes next is sometimes called the degenerate era. The universe will be populated by white dwarfs, cooling toward absolute zero, neutron stars and black holes drifting in the dark, and stray planets and asteroids wandering between dead stars. There will be no more ongoing energy production. Life, in any biological form, will become impossible. This sets a hard limit on the search for civilizations. Life, as we understand it, can only exist during the era of stars. That era began about 13 billion years ago when the first stars ignited, and it will end roughly 1 trillion years from now when the last red dwarfs go dark. We are currently about 13 billion years into a window that lasts 1 trillion. We are in the early part of cosmic history. This is the early hypothesis we touched on earlier, but it has a darker layer when you focus on the end. The window for life is closing, slowly, every day. Every star that goes out is one fewer chance for biology. Every cooling planet is one less opportunity for civilization. The clock is ticking, even if we are far from midnight. The temporal Fermi paradox interacts with this in a strange way. If life is rare, the early part of the cosmic window is when we would expect to see it. New stars are being born. Heavy elements are spreading. Planets are forming with the chemistry needed for biology. Conditions are good. If civilizations are going to arise, this is the time. If life is common, then the window should be loud with intelligence. We should hear voices everywhere. We should see fingerprints across the galaxy. The fact that we do not, during the most fertile period of cosmic history, suggests one of two things. Either life is much rarer than we think, or something is silencing it. Now, look forward. As the universe ages and stars die off, the conditions for life become harder to maintain. Planets cool, energy sources dwindle. Even if civilizations existed in the far future, they would face challenges we cannot easily picture. The cost of maintaining biology in a dying universe would grow. The rewards would shrink. Eventually, the window closes entirely. The last star fades. the last planet cools. Whatever civilizations remain, if any, would face an absolute end. Not extinction by accident or choice, but extinction by the laws of physics. The universe itself becomes uninhabitable. We are in the middle of the window now. The opening was billions of years before us. The closing will be hundreds of billions of years after us. Somewhere in this vast span, life rises, looks around, and either finds company or does not. So far, every signal suggests we have not found company, and the window keeps narrowing. Imagine being the first guest at a party that is supposed to last for trillions of years. The lights are on, the food is laid out, the music is playing softly. Other guests will arrive, but not for billions of years. You walk through the empty rooms wondering if you got the time wrong. This is one possibility for humanity. We may be the first. The math behind this is real and worth taking seriously. The universe is going to support life-friendly conditions for hundreds of billions, possibly trillions, of years. Most of the stars that will ever produce intelligent species have not yet finished forming. Most of the planets that will ever host civilizations are still cooling from their early molten state. We exist during the very beginning of the window, the first 13 billion years out of a window that may last a trillion. By the math of when intelligence is most likely to appear, we are absurdly early. If we are first, then the silence has a simple explanation. There is no one else yet. The galaxy is empty because life has not had time to develop almost anywhere. We are not the last surviving witnesses of a long line of civilizations. We are the opening act of a show that will run for 100 billion years after we are gone. This is a strange kind of comfort. It means the silence does not predict our doom. It does not mean civilizations all die. It just means civilizations are rare so far, and the future will be different. Eventually, the galaxy will fill up with thinkers, builders, and explorers. Eventually, the radio noise will be deafening. Eventually, the universe will be the busy, crowded place we expected it to be. But humanity will not be there to see it. If we last another billion years, we will have witnessed the birth of perhaps a few other civilizations in our galactic neighborhood. If we last 10 billion, we might see a galaxy starting to fill up. To see the universe fully populated, we would need to last 100 billion years or more. That is far longer than any species has ever lasted on any planet we know of. So the early hypothesis offers a strange consolation. We are alone now, but the universe will not always be lonely. Future civilizations will look back at us and wonder about the species that came so early. They will study our ruins, if any survive, the way we study ancient cave paintings. They will marvel that anyone managed to develop intelligence so close to the cosmic dawn when conditions were still wild and unstable. There is also a darker reading. Being first means having no one to learn from. Every other species in the universe, eventually, will have the option of looking back at the records of those who came before. They will inherit the wisdom, the warnings, and the technologies of previous civilizations. They will not have to figure everything out alone. We do. We are inventing technology with no precedent. We are facing problems no one has solved. We are making choices about energy, intelligence, biology, and survival, without the benefit of any older civilization's example. Every mistake we make is one we have to make ourselves, the first time, with no manual, and every mistake could be fatal. Other civilizations, in the distant future, will inherit a galaxy already full of clues. They will find the ruins of those who came before. They will read the chemical fingerprints of dead worlds. They will piece together the history of intelligence in their region. We have none of that. We look up at the stars and find them blank. Being first means walking through a dark room with our hands out, not knowing what is in front of us, with no one to ask. If we make it, future civilizations will rise on the foundation we leave behind. They will learn from our successes and our failures. They will be the children of the galaxy we are barely beginning to map. If we do not make it, we will be the first ghost in their cosmic record. the first warning, written in faint chemical traces across a planet they may someday visit, telling them what not to do. Either way, the silence is not just space, it is responsibility. After 32 chapters of math, hypothesis, and cosmic history, the question always returns to the same place. Why is the galaxy silent? There are answers, there are theories, there are mathematical models, statistical arguments, and philosophical frameworks. Each one offers a piece of the puzzle. None of them is complete. But there is one answer the temporal Fermi paradox keeps pointing toward, and it is the darkest of all. The silence is not a coincidence. It is not a gap in our search. It is not a quirk of timing or distance. The silence is a pattern, and patterns this consistent, this widespread, this old, are not random. They are warnings. Consider what we have learned across these chapters. The galaxy is old. Civilizations should have arisen many times across its history. Detectable broadcasts from any of them should still be reaching us, given the time available. Probes from any expansion-minded civilization should already have saturated the galaxy. Megastructures from energy-hungry species should be visible in our telescopes. Chemical fingerprints of past industrial activity should be readable in the atmospheres of distant worlds. None of these things have been found. The standard interpretations are that life is rare, that civilizations are short, that distances are unbridgeable, or that we are looking in the wrong way. All of these may be true, but the consistency of the silence across every method we have tried, across every region of the galaxy we have surveyed, is striking. It is as if the universe is engineered to be quiet. If the silence is engineered, the question becomes, who or what is doing the engineering? There are several possibilities, each more disturbing than the last. The first is that a great filter exists, sitting somewhere along the path of technological development, and it stops nearly every civilization that gets close to it. We do not know what the filter is. We only know it works, almost every time. The silence is the sound of countless civilizations hitting that wall. The second is that civilizations destroy themselves. Every species that develops powerful technology eventually develops the means to end itself, and most of them do. The window of detectability is brief because intelligence, once it crosses the threshold of powerful technology, has a high probability of self-extinction within a few hundred or thousand years. The silence is the cumulative result of every civilization in the galaxy choosing accidentally or deliberately to end itself. The third possibility is that something out there actively silences civilizations that become loud. Whether that something is a single advanced species, a network of older civilizations, or some kind of automated defense system, the result is the same. Civilizations that broadcast are quietly removed. The silence is not natural, it is enforced. The fourth is that the universe itself produces silence as a feature, not a bug. The brief lifespans, the vast distances, the brutal arithmetic of synchronization may all be working together to ensure that no civilization ever truly meets another. The silence is built into the rules. None of these answers are good news for us. We are doing exactly what every previous civilization in the galaxy may have done. We are broadcasting. We are expanding. We are starting to build technologies that could attract attention or destroy us, possibly both. We are walking the same path that, as far as we can tell, has led every other intelligent species into silence. The silence is the warning. It is the data we have to read. Every empty radio channel, every unfound probe, every quiet star system is a piece of evidence that something happens to civilizations like ours, something that prevents them from being heard or seen or remembered, something that we are heading toward, whether we know it or not. We do not know what comes next. The temporal Fermi paradox does not give us a roadmap. It only tells us what we should expect if we keep doing what every previous species apparently did. We should expect, eventually, to go silent. The question is not whether we will go silent. The question is what we do with the brief time we have left in our window. Do we burn brighter, or do we learn from the cosmic silence and try to do something different? Do we keep broadcasting into a galaxy that may already be listening with hostile intent, or do we go quiet ourselves, voluntarily, the way the older civilizations may have done? There are no easy answers. There may be no answers at all, but the silence is talking to us in its own way, and what it says is uncomfortable. It says that thinking species like ours are rare, brief, and easily ended. It says we are not the first to ask these questions, and we will likely not be the last to fail to answer them. The galaxy has been quiet for 13 billion years. We have a few hundred more, at most, to figure out why.